Hey guys, so today we're going to get into the beginnings of vector kinematics. And so to do that, what we're going to do is I'm going to do the two lessons today are going to be all about dealing with vectors, addition of vectors, and it's going to review some of the mathematics that you should have learned at some point in the past. I can't remember if it's part of grade 10 or grade 11. If you're here in physics 12, you should have seen it though already. So today is going to be less of a lesson in physics and more of a lesson in math, which should make some of you very happy, I think, from what I understand. So here we go. First, we're going to review the law of sines. Now, the law of sines is just this. It's sine A over A equals sine B over B equals sine C over C, and this thing works for any triangle. And what that means is the sine A, this is an angle, and this A is the opposite side. And this ratio holds true for all combinations of sides and angles. So you can use any two of them to help you find something that you need. But you need angles and their opposite sides. So example would be something like this guy here. If I've got this triangle, they don't have to be right angle triangles. We've got a 15-degree angle, and we're looking for, so this will be the opposite side here. That's what we're looking for. And we've got these two guys here, 25 and the opposite side there. So because we have angle and opposite side and another angle, and we're looking for the opposite side, this would be a classic example to use law of sines. Hoping this is review. This isn't, please let me know. What we can do is we can set up this ratio. The ratio goes something like this. We've got the sine of 25 degrees divided by the length of the opposite side, so that's 8. And that's going to equal the sine of 15 degrees over the opposite side, which is x, which is what we're looking for. At this point, you're all in physics 12, so we should be able to solve that relatively easily. We're going to multiply the x up. We're going to divide sine 25 down, and we're going to multiply the 8 up. So we're going to get something that looks like this. X equals 8 times sine 15 over sine 25. Again, the x we're looking for gets multiplied up, this gets multiplied up, and the sine 25 gets divided down. So if we run that through, we're going to get something that looks like this, that x is equal to 4.9, and that's a side length. This side length was in meters, so this guy's also going to be in meters. Believe it or not, this is a useful formula that we're going to want to have access to relatively easily. I'll give you another example if that would help. We've got a few things that we're looking for here. We've got a 40-degree angle, and we have the opposite side. We have a side, and we're looking for, well, two angles here, x and y. I don't have this length here, and because this isn't a right angle triangle, I cannot use Pythagoras for this guy here, because this is not a 90-degree triangle. So what we're going to have to do is we're going to have to find this side first. Sorry, we're going to have to find this angle first, and then use this law of sines again to find this guy down here. So we can run this thing through. We're going to have the sine of x divided by 4, and that's going to equal the sine of 40 divided by 5. To solve this one, we're going to multiply 4 up, so we're going to get sine x equals 4 sine 40 over 5. And then to isolate x, what we're going to do is we're going to take the sine inverse of both sides, something that you should be able to do. So this is going to become x equals the sine inverse of 4 sine 40 over 5. And this one I will show you how it goes into your calculator. Doesn't matter if you've got a scientific calculator, a two-line display scientific calculator like I recommended, or if you've got a graphing calculator, it's going to look the same. So especially if you're using this one here, sine inverse of 4 sine 40, make sure you close the brackets properly. So that bracket's going to get closed there. divided by 5, close the bracket again. So I've got, go back to the beginning, the sine inverse of 4 sine 40 over 5. And we're going to get that x is 30.95. If you go back and look at this thing, x is an angle, so that's a measurement of degrees. And then the last step here to find y, we know that the angles in a triangle add up to 180. So this guy is going to be 180 minus 40 minus 30.95. That's going to give us 180 minus 40 minus 30.95. 40 minus. It's going to give us 109.05 degrees. We're done. Okay. So that's sine law, using it to find angles and sides depending on what you're given. So I'm going to leave you guys. I want you to try this example right now. This is what I would do if you were all sitting in class. So pause the video real quick. Do these, or do this triangle down here. You're looking for a bunch of side lengths here. I believe in you. You can do it. The one piece of information that you're likely going to need is this guy here. But again, we all know what the angles in a triangle add up to, so you can do that one there. Pause the video right now, and then I'll write down the answers. So I got that y equals 10.6 meters and x equals 13 meters. This formula is one of the ones that I'm going to get you guys to write onto your formula sheet. So grab your formula sheet. You should all have your own. I'll put my name up here. This is Dawidoff's formula sheet. And let's add some mathematical formulas here. Just so you don't have to hang on to this one, we're going to write it down. Sine A over A equals sine B over B equals sine C over C. There it is, sine law. One of my math profs once told me that, my physics profs told me that a good physicist is a lazy physicist, and why memorize things when you, we just want you to know how to do them. So we get the formula sheet here. We don't have to memorize these formulas. We just need to know how to do the things with the formulas. Because out in the real world, you're doing physics or engineering or whatever, you're going to be able to look stuff up. But you want to have things relatively quick and easy to access. So let's at least know where to look. So we got sine law. We've also got cosine law. Cosine law looks like this. C squared equals A squared plus B squared minus 2AB cos theta. Now, it's important to recognize, though, that these guys, C and theta, are a side and the opposite angle. Again, just like with sine law. So sometimes you'll see this thing written as C squared, big C squared equals big A squared plus big B squared minus 2AB cos little c. Sometimes you'll see it like that. And actually, I'm going to write it differently with lowercase c's here and a big C here, just so we can line it up with how I did sine law. So I'm going to rewrite this. This is how we're going to use it. That little c squared equals lowercase a squared plus lowercase b squared minus 2 little a little b cos big C, and these two are angle and opposite side. Okay, so let's do one example of this. We're going to do this guy here. What it requires is that you have this side angle side, and this page came from one of my previous physics teachers because I thought I had some good examples. And so his way of explaining it was you want to look for the mouth. You want to find an angle on the two sides that open to, and have two adjacent sides that open to an opposite side. So you've got that here. So we can use, in this situation, we can use cosine law. So let's fill it in. We've got an angle and then opposite side. And I've got two adjacent sides. So we're going to have x squared equals, and it doesn't matter which of these is a and which of these is b. This is, it looks a lot like Pythagoras, but this is useful for any triangle. It does not have to be a right angle triangle. So this is going to be 13 squared plus 8 squared minus 2 times 13 times 8 cosine of 15. So this you can just run through your calculator. X is going to equal the square root of this whole thing, 13 squared plus 8 squared minus 2 times 13 times 8 goes 15. This can all go into your calculator in one long shot. If you do that, you're going to get that X is 5.7 meters. Relatively straightforward. Okay. Yeah, and that's the situation that these things need to show up in. I'm not going to do B or C. I don't think I need to do B or C. I'm hoping that this is review. Again, if it's not, please make a note on here. You don't. Lots of you are making private, putting private questions. That's great if you don't want some anonymity. But I would encourage you to make your questions public posts so that you can respond to each other. So you're not just necessarily waiting for me, and so that I can make public responses to address some of these questions. So if we look at B and C, I'm not going to do them, but I want to talk about them. If we look at B and C, we can use cosine law. We've got a side, an angle, and a side, an angle wedged between two adjacent sides that we know, and we can use that to find this value here using cosine law. Once we do that, we'll have two adjacent sides and then an opposite side, and we can use cosine law to find this angle here. So I'm not going to run it through. I want you to try it. If you do that, so pause the video here, and I'll have the answers for you. Give me one sec. So I got these two values. Hopefully they line up with yours. If you got something different, let me know. Like I said, I could have made a mistake. I kind of doubt it. I shouldn't say that. I don't think I made a mistake. Yeah, I think my work's good, but by all means, please check it. If you got something different than I did, let me know. But yeah, anyway, so that's sine law, sines law, cosines. We're going to add the law of cosines as well to your formula sheet. Let's toss it up here right beneath the law of sines. So we're going to have little c squared equals a squared plus b squared minus 2 little a little b cos big C. That'll be a useful tool for us as well. And heck, while we're at it, why not just add this relationship in here? It's going to be useful. One more trig relationship. The tan of theta equals sine theta over cos theta. And because for some reason students still need this, we're going to also add SOHCAHTOA on here. This is how I write it. So there we go, a whole bunch of trig and a bunch of trig relationships that we're going to need here. I do still have to write these down for Physics 12, so that's okay. We've got space. We're going to put one more on here, but we're not going to do that yet. We will use that extra formula that is missing in a little bit here. So what I want you guys to do is part of your homework is to do some of these. I know some of you are going to be better with this stuff than others. I want you to do odds on all of this. So it's going to give you 1 and 3 here. It specifies law of sines. And if you fill up the page, you're going to do 5 and 7, which specifies using the law of cosines. And then it's going to give you, 2 more questions, 9 and 11, and it says solve either triangle using the law of sines and cosines. So that's 6 questions. It's not a lot, not a big ask, and it's definitely good to do some review on these mathematical concepts that might have been a long time since you've seen them. Then, we've got the answer key for those right here. So answer key, sorry, I just had to pause the video because someone came in here. So we're going to jump now into, I don't know why that blank page made it in there, but it did, it's okay. looking at vectors in polar form. And so the law of sines, law of cosines, it's going to be useful as we start to solve these things here. So this, sometimes Mr. Morrison goes into some detail with vectors, and sometimes he doesn't. I'm not sure what you've seen and what you haven't seen, so we're going to do a proper treatment of this. So there are two forms that vectors show up in. One is polar form, and the other one is rectangular form. We've already kind of seen rectangular, and well, you've seen polar too. You don't necessarily know that that is what it's called. So we want to recall that we said in lesson 1 a vector quantity has a magnitude and a direction. We're going to do some operations with multiple vectors using magnitudes and directions and that kind of stuff. So first example, let's just get into it. An object is moving east at 2 meters per second. It accelerates north at 1 meter per second squared for 2 seconds. What is its final speed? So we're going to draw in this lined area kind of what's going on here. I've got an object. There it is. And we're told two things. It's moving east at 2 meters per second. So I've got v 2 meters per second. It's given a northward acceleration. A equals 1 meter per second squared. And so what we want to find is this. You have an idea what's going to happen, right? It's moving to the right. Let's give it an upward push. So it's going to have a velocity that looks something like this, and this is what we want to find. So all of the kinematic equations that we've been using, we can't use in the same way that we've been using them up to this point, because for all of that stuff, the acceleration has either been perfectly parallel to the velocities, or it's been perfectly anti-parallel. Like it's either been in the same direction or the exact opposite direction. So now we've got an acceleration and a velocity that are acting, well, in this case, they're perpendicular to each other. So we have to figure out what we're going to do with that. If we look at that kinematic equation, though, we're going to write down, so we've got a velocity initial. I'm going to add some subscripts, and a velocity final, and we've got an acceleration. We also have a time, t equals 2 seconds. So we're going to put that in here as well. You know that it's accelerating, t equals 2 seconds. So I'm going to look at the formula. We just can't use it the same way. We have Vf equals Vi, again, vector notation, plus A times t. Well, what do we do with that? We're going to see here really shortly how this ends up getting dealt with. One second. So we haven't looked at how vectors, so let's look at the formula here. We're going to have a vector multiplied by a scalar, so an acceleration times a time, and then it's going to be added to the initial velocity. But how we add vectors together is not something that we've looked at yet. So we're going to use, this is the setup, we're going to use kind of a hand-wavy argument here to talk about what this is going to look, what the final answer must be given these three objects. So this thing has an initial velocity of 2 meters per second. It's being pushed up here, so it's not going to lose this component, but it's going to have some upward velocity added to it. So if we look at this thing, the answer cannot be 0. The other thing it can't be is 4 either, because if you look at what's happening here, the 1 meter per second squared acceleration for 2 seconds, this a times t, is perpendicular to this initial velocity here. So because it's perpendicular, they're not going to add the way we would expect them to add. You can't just add this direction and this direction together algebraically and expect them to work out here. So the 1 times 2 is going to be 2. The initial is 2. So 2 plus 2 is 4. But vectors don't add that way. And I'll show you here in a second. So, but just using this argument, we also know it can't be 4. So it's got to be B. But without doing any math, we don't know 100% for sure, but that's okay. We're still going to come back and we're going to, I will come back and I'll show you, once we look at how we add vectors, I'll show you that this is right. So we're going to represent vectors as arrows, which we've already done. We've used them in Physics 11 to demonstrate, the direction that the velocities are in or the accelerations are in. But we do that for a reason. We do that because vectors can be represented by arrows like this. They're mathematical objects represented by arrows. The end of the vector is called the tail. So you get to the beginning of the vector, and the tip of the vector is called the head. So it's also just called, sometimes it depends on the physicist or physics teacher you're working with. Sometimes it's called tip and tail. Sometimes it's called tail and head. I will probably actually just use tip and tail because that's how I was taught. So here we go. Let's do some stuff here. We're going to draw some vectors. We're going to draw a coordinate system. We're going to put the tail at the origin. I'm not going to actually use a protractor. We're going to do some estimating here. We're going to estimate the angle. We're going to estimate the length. I'm not going to require ruler and protractor. But you want to make an effort to make a good guess. So for example, here we're going to draw an acceleration that's 3 meters per second squared, 40 degrees west of north. So here's my coordinate grid. And you are going to want to draw these. Typically, we will draw them much smaller than we will do right now, but to start, we're going to draw them big. And so remember, we're going to label all these things. We have north and south go that way. We have east going that way. We got west going that way. So there's my coordinate grid. Now I want to draw a 3 meter per second squared vector, 40 degrees, and that says W of n means west of north. It means we start at north and we go over 40 degrees. Because we're starting at north and we're going west of it. Now, perfectly like that would be 45 degrees. So just a little bit back is going to give us our 40 degrees. And so we're going to call that a 3 meters per second squared, and we're going to label this down here 40 degrees. So that is how I would draw a acceleration vector that's 3 meters per second squared, 40 degrees west of north. And the length of this vector directly corresponds to that value. Okay? So if I had another acceleration vector that was 1.5, it would be half the length. If I had another one that was 6, it would be twice the length because 6 is twice 3. And 1/2, or 1.5, yeah, 1.5 is half of 3, so it would be half as long. So the length of the vectors, how you draw them, is actually important. We don't want to just slap vectors down and call it good because that'll radically alter the math that we have to do with them. We're going to use sine law, we're going to use cosine law to figure out lengths of vectors as we start to combine other vectors. So make sure you are a little bit meticulous here. So in one coordinate system, we're going to draw these 4. So here's my coordinate grid. We're going to make it nice and big. We have the space. Let's use it. That should be a straight line. It's not. I'm sorry. There's that. So we've got north. Zoom this out here so we can put them all on here. South, east, and west. Now, when we actually use this in a physics problem, it's going to be much, much smaller. I'll show you how it works. But for the sake of this, let's make them big. So we'll do this guy in red. My 20 newtons, so that's a force vector, 40 degrees east of north. So the first thing we got to do is establish what east of north is. So you always start at the second direction and then go blank of it. So if we're starting at north and we want to go east of it, well, east is to the right, so we're going to go here, something looks like that. And this one's going to be 20. So let's look here. I've got a 20, a 5, a 15, and an 8. Okay, so the 20 is the biggest one. So we're going to make something looks like this. So that is a 20 Newton vector. And this guy is 40 degrees right there. Okay. Let's do this next guy in pink. I have a 5 meter per second, 10 degrees south of east. Okay. Well, the value of the vector corresponds directly to the length of the vector that we draw. So 5, if this is my 20, I need to draw a vector that's 1/4 the length to represent this 5 meter per second vector. Okay. I want 10 degrees south of east. So start at the second direction, east, and we're going to go south of it. 10 degrees, not very much. So we're going to have something that looks like this. And we want it roughly quarter the length. So that's half, so that's a quarter. That's basically it. That's pretty good. It doesn't have to be exact, but it's got to be close. Like, make a good estimate. And this guy in here is 10 degrees. This next guy in orange. I want 15 meters southwest. Well, due southwest means exactly halfway between south and west. This is 90, so halfway is 45. So something, and it's 15. 15 is 3/4 of 20, so we want something that's 3/4 the length. So it looks like that. Something looks like that. So that's our 15-meter vector at 45 degrees. And it doesn't matter if you put the 45 there or you put the 45 there, because they're the same. It's just southwest. The reason I put it there is because, well, I'm following the instructions I gave you before. You start at the second one, and then you go the first direction from that. So I started at west, and then I went south. So due southwest is 45 degrees there. And then the last one here, I'm going to do in green. 8 meters per second squared to 20 degrees north of west. So we start at north. We go up 20 degrees, and it's 8. So 8 is going to be, well, halfway. Oh, I didn't put the length on that one. This one's 5 meters per second. 1 second. Let me pause this. Okay, someone just asked a question. Anyway, back to this. So I want an 8 meter per second squared, 20 degrees north of west. So I want it halfway between 5 and 10. So it's going to be longer than this, but not quite halfway. Half as long as the red one. And I want 20 degrees north. So if that's 10, maybe a little bit more is 20. So something looks like this. Yeah, it's a little longer than 5, and it's a little less than halfway. Yeah, so let's call that good. There's my estimate. That's an 8 meter per second squared, 20 degree north of west vector. So we have something that looks like that. Okay, you got to be meticulous. You got to be purposeful with how you draw these things. Flip the page. Let's look at how we do some algebra with these things. So if we're going to multiply vectors, what we're going to end up doing is we're going to multiply the vector magnitude by the number. Sorry, let me be a little bit more specific here. We're going to multiply vectors by scalars. Okay, so we're going to take a vector, we're going to multiply it by a scalar. We can, or I'll say it this way, we could, but we will not. We will not. For those of you who have taken IB math, we will not multiply vectors by vectors. I know you know how to do that, and that's great. Vectors with other vectors. Okay, not going to teach you how to do it. We don't need it. It's beyond the scope of this course, and they'll teach you how to do that when you hit university. For those of you who have taken IB, what I'm talking about here is so multiplying vectors by vectors. I'm talking about cross product and dot product. You've seen it. That's great. We're not going to use it. Don't worry about it. What we're just going to look at is scalar multiplication. So we're going to take vectors and we're going to multiply them by scalars. But how that works is this. I want to multiply the vector by the magnitude of the number. So in this case, we have the scalar here. When I say the number, this is the scalar. And when we say vector magnitude, I mean the length of that vector. If the number is negative, so if the scalar that we're multiplying by is negative, we reverse the direction, otherwise the direction doesn't change. The direction stays the same. If it's negative, it flips. If it's not, it stays. So I've got my vector v. What I want to do is I want to draw a vector that is 2 times, so my scalar here is 2 times v. Sorry, phone's ringing. 1 sec. Okay, sorry about that. So I want to draw a vector that's 2 times v. So here's my v. I'm going to draw a vector that's twice as long. So let's start. And it's positive 2. So it's going to be the same length. Sorry, it's going to be the same direction, but twice the length of this guy here. So I'm just going to draw in parallel to it. So there's my, that's v, same length. And now I'm just going to double it. There's 2v. Basically twice the length. Let's draw half of v. Well, it's going to be half the length, same direction. There's my 0.5v. Negative v. Well, that's a -1 times v, so that just means the vector is the same length, but the opposite direction. So I'll put that over here. There's my -v. And I want -2v, so it's going to be flipped and twice as long. So I'll have a vector that looks like this. -2v. Relatively straightforward, I think. Okay. So that is multiplying vectors by scalars. Now we're going to add vectors. This one is a little bit different. And this is where it becomes really important that we estimate properly. We draw them properly. So those of you who are artists and are meticulous about that kind of thing, you're going to do really well here. Those of you who just slap and dash and draw things down, and yet it's going to be painful for you. We want to make sure we do this well. Otherwise, things are going to get weird. So to add vectors, here's what we do, step by step. We draw the first vector. Then starting at the end of the first vector, so when we say the end here, I don't want to use that. Starting at the tip of the first vector, we're going to draw the second vector. The sum of the resultant goes from the tail of vector 1 to the tip of vector 2. So the resultant is just, you add two vectors together. What is the answer? That's the resultant. We want to measure the angle at the tail of the resultant, so you can measure it or calculate it using sine law, cosine law, or various trig relationships. We're going to use all that trig that you've done. We're going to measure the length of the resultant or calculate it using sine law, cos law, or various trig relationships, as was stated down here. Okay, so let's do an example to see what this looks like. So I've got R1, that's just vector 1, and it's 3 meters northeast. I've got R2, 2 meters, 30 degrees south of east. What I want to find is R1 plus R2. Here's how you're going to do it. First thing you're going to do is we're going to draw R1. Okay? So now we're going to draw, instead of having just the gigantic coordinate grid, we're just going to draw a tiny one at the tail end of each vector. So down here, if we look what's happening here, we're going to have a vector that goes northeast, and then we want one that's south of east. So it's going to kind of go up and then down again. So just to get an idea of what these things are looking like, so I can position it on my page properly. Northeast and then south of east. So down here, little coordinate grid. And then I want 3 meters due northeast. Okay, so my 3 meters, and draw big. One of my physics profs always told me, he said, draw it, erase it, draw it bigger. It's never going to be quite as big as you're never going to draw it quite as big as you should. So you've got the space, use it. Here's a 3 meter vector. Okay, and due northeast, this angle right here Because I know what's going to happen here, I'm gonna write it in like this. This angle here is 45 degrees, and this is 3 meters long. Okay, so it's first. Now to add R2 to it, we're going to start at the tip of the first vector we've drawn. So we go to the end of it, the tip of it, and then we're going to draw the second vector. So at the tip of this, I'm going to add another coordinate grid. This little guy. And then we're going to draw R2. So I want 2 meters, 30 degrees south of east. So 30 south of east, start at east, go down 30. So it's going to look something like this. And it's 2 meters long, so that should be 2/3 this. Want something that looks like that should be 2 meters. And we know that this angle right there is 30 degrees. So then our resultant R1 plus R2, we start at the tail of the first vector and go to the tip of the second vector. So it's going to be something that looks like this. And if at this, a ruler is not a terrible idea. If you can freehand it, great. I can't really. So I'm just going to grab a ruler, draw a line between there and there, especially when it's this big. So it goes from the tail of the first to the tip of the second. So this vector here is going to be my R1 plus R2 vector. Now we want to figure out how long that is. So to do that, we're going to use a bunch of the relationships that we've looked at before, or that you should have looked at before in math. So here we go. I want to figure out how long this is. If I'd been using a protractor and a ruler, I could just measure that and be done. Okay. In fact, I will. Let's see how good we are, because we're gonna. You know what? No, I'm not gonna do that. Never mind. That just makes things more confusing. We're gonna use sine law. Cosine law. We're gonna calculate this thing. Okay. So we need 2 pieces. We have no angles, so it's gonna be complicated. We have 2 sides though, and we're looking for this side here. So I've got these 2, and I want this one. So if we can figure out what this angle here is, we could use cosine law to find this. Okay, so let's at least make an effort to talk this through. If this here is 30 degrees, from this black line to this black line is 90, that's going to make this piece here, actually I'm going to use orange for this, that's going to make this piece here 60 degrees. Okay. The next piece we're going to use, I can't remember where in the math curriculum it is. It's either in grade 10 or grade 11. They look at angle relationships. So if you've got something set up like this, just geometrically, I've got this is perpendicular, this is this is parallel to this, and you've got a line between them. This is called alternate interior angles. So if that's 45, this guy here must also be 45. So what that tells us is that this entire angle here is 105 degrees. Okay. So we can use cosine law. Now we've got the angle, we have these 2 sides, we can use cosine law to find this. So I'm going to call this R3 just to simplify my notation. So we're going to have R3 squared is going to equal 2 squared plus 3 squared plus 2 times 3 cos 105. Using the cosine law that we wrote down on our formula sheet. So R3 rather is the square root of this whole thing. I'm not going to write that out again. But on your calculator, I'll show you what it would look like on a calculator. So we're going to do the square root of 2 squared plus 3 squared, no, I'm sorry, the square root of 2 squared plus 3 squared plus 2 times 3 cos 105, close the bracket. And if I go back to the, I can scroll back to the beginning, I have to close that bracket there as well. This would be a lot simpler on a graphing calculator because the screen is much larger, but you don't need it. And there we go. We have a length of, guys, I screwed this up. Hopefully you're all yelling at the screen. That should be minus 2 squared plus 3 squared minus, guys, I'm sorry. But this is easy to fix. Up here, minus, there we go. That's the answer I should have gotten. Easy to fix. This is why you want a 2-line display of scientific calculator, so I can go back and I can see my errors. So that's going to have a length of 4.01 meters. And I got to find the direction. Okay. We have this angle here is 105. So we can go back now and we can find the direction of R3. To find the direction of R3, what you need is the angle at the tail end of the vector. So what I want is the angle between any two of these cardinal directions here. Like, so I've got north and I've got east here. I want to find the whole angle either from north to the red line or east up to the red line. So to do that, though, I'm going to need to find this angle right in here. I can use sine law to do it. So we're going to call this, I don't know, let's call it big R. So I want the sine of big R, and on the opposite side is 2. You know all your sine law practice. This is why we practice the sine law and the cosine law. So sine R over 2 equals, and the only other side relationship that we have is this guy here, 105 and 4.01. So it's going to be the sine of 105 degrees over 4.01. So we're going to find that that side, or that angle R, is 28.8 degrees. So this guy here is 28.8 degrees. Now we're almost there. What that means is this. It means that the total angle, I'm going to make my coordinate grid a little bit larger here. When we're referencing the direction for our vector, we have to go from the cardinal directions. So I got north and I got east. So either I need this whole angle, I'm going to use green because it's away from me. So it's either this whole angle here or this little guy in here. Okay. Well, this whole angle here, we got 45 to there and we got 28.8 to there. So that's going to be 73.8 degrees. Or we could go up from east or north from east. If we do that, if this is 73.8, this is going to be 90 minus 73.8. That's going to be 16.2. So there's two different ways we can quote our answer. Either this is 4.01 meters, 73.8 degrees east of north, i.e. we started at north and we went east, or it's 16.2 degrees north of east. It doesn't matter which one you use, east of north or north of east, but you must use one of them because it's a vector. It has to have a magnitude and a direction. That's it. Okay. So what I'm going to do now is we're going to go back and we're going to finish that problem we started right at the beginning. What do I do with this? Well, you can see using our kinematic equation, I have a vector times a scalar plus another vector. So we're going to have two pieces here, the multiplication piece and the addition piece. So let's put this together. I've got V1. Here's my V1. It's 2 meters per second, and we're told that it's east, so it's just flat. We're going to add to it acceleration times time. So the acceleration times the time is going to be 2 times 1. So I want a vector that's too long, and seconds times meters per second squared actually is going to give me a velocity. So my seconds are going to cancel, and I'll get something that's meters per second. 1 times 2 is 2, so I'm going to have one that looks like this. Starting at the tip to tail, we have the acceleration times the time vector. Looks like that. So then my resultant vector goes from the tail of the first to the tip of the second. This one's east, this one's north, so they're perpendicular to each other. So I can just use Pythagoras for this. I don't need cosine law because that's a 90. So we can see that this thing is going to be, we'll call this VF because that's what it is. VF is going to equal the square root of 2 squared plus 2 squared, which is the square root of 8, which is 2.83. And because these two lengths are the same, we know this angle there has to be 45 degrees. So our final velocity, VF, is 2.83 meters per second, 45 degrees north of east. Or we could have just said northeast. The final speed is just the 2.83. If I want it as a vector, I need the magnitude and the direction. That would be that there. There it is. We've got one more example here. We're not going to do example 6 or example 7 because I've got lots of practice for you. Based on what I just did with going back to the first one, I want you to try that on your own here. So this is going to be part of your homework. I'll tell you what the answer is so that you can verify that you've got it properly. I don't have the values exactly, but what I've got is this. You want the square root of 45, and you want the tan inverse of 6 over 3 south of east. So that's what I've got for you. See if you can get that. For those of you who are in a math class right now, make sure your calculator's in degrees, not radians. That's my pro tip for you. Okay, so this is going to be part of your homework. I'm just going to flip over here. This is all homework. Adding vectors head to tail. This is homework. I'll give you answers here as well. Let's put them on the left. This one's 13.89 centimeters, 30.26 degrees north of east, or 59.74 degrees east of north. This one is 48.8 kilometers. We got 55.1 degrees south of west. I'm not going to put the other one. I mean, you see it's 90 minus, right, to get there. You guys are smart. You can figure that out. There's my displacement there. This one's going to be 33 kilometers due east. This one's going to be 249 kilometers, 16.1 degrees north of east, or 73.9 degrees east of north. This one's going to be 9.4 kilometers, 15.8 degrees north of west, or 74.2. And again, you don't have to put both answers. I'm just providing both of them because if I give you one, you guys are inevitably going to ask me about it. So there's that. This is also part of your homework. There's A, there's B, and I want the sum of them. So I'll put the answer down here. It's going to be 5.09 kilometers, 70 degrees north of west, or 20 degrees west of north. And then this answer here for number 2 is going to be this, 29.2 kilometers, 83.1 degrees north of east. So you've got a fair bit to do. I want you to practice sine law and cosine law. Oh, no, and there's number 3 here. Oh, no, this lesson keeps going. Maybe I'll only do one lesson today. This guy is going to be 87.32 kilometers, 43.14 degrees north of east. So that's all addition of vectors. This lesson isn't actually done, but I've got a bunch of homework in here. So what I would recommend you do at this point is pause and do these questions and then come back to this video. Because there's one more algebraic expression we have to do. We have to do subtraction of vectors. We've done multiplication, we've done addition. Now we're going to do subtraction. Subtraction is actually easy. Subtraction, if we look at this, I don't like this term opposite here. We're going to use this term when I add the negative. Because I had something like a minus b is the same as a plus negative b. And when I'm dealing with my pre-diploma Math 9s, this is how I prefer them to write it. They love to write it like this. When you're adding a negative, it's plus the negative b. I always make them go back this way. But now, when we're dealing with vectors, it's actually better to write it like this. We know what a negative vector is. It's the same length as the previous vector, but we're just going to flip the direction. So let's just do a couple examples here. Relatively, just 2 examples really quick. For the vectors a and b, we want to find a minus b. So there's a, there's b. So a minus b is going to look like this. We don't have lengths. All we're doing is drawing the relationship. So I'm going to draw a. A minus b is a plus negative b. So there's my a. Sorry, someone's knocking at my door. Got to pause. Sorry about that. Right, so we've got a plus negative b. I'm going to do negative b. I'll do that in green. So again, negative b is just the same length, but I flip the direction. So negative b is going to look like that. Here's my negative b. So this guy here, again, start at the tail of the first and go to the tip of the second. So this guy here is my vector a minus b. Easy. So let's do an example using some values. We're not going to do this. We're not going to do a from example 10. We're just going to go straight to the end. Okay, here we go. So I want to find the acceleration vector a, given that the acceleration is your final velocity minus your initial velocity divided by your change in time. So here's my final velocity in green, my initial velocity in blue. So let's draw this out first. I want VF minus VI. So that's going to be VF plus negative VI. And I guess I shouldn't have, yeah, whatever. So here we go. VF is 2 meters per second north. So it's going to draw a north vector. There's 2 meters per second due north. And this one's going east. So on these ones, I didn't have to draw my little coordinate grid because it's north and east perfectly. If it was weird angles, I would have. So VI is 3 meters per second east, but I don't want VI, I want negative VI. So I'm going to draw a 3 meter per second vector west, the opposite direction. And 3 meters is a third longer than 2, so I'm going to draw one that's a little bit longer than 2. Maybe something looks like that. There's my 3 meter per second vector. So this guy here is going to be VF minus VI. So north and west are perpendicular to each other. So I can use Pythagoras to find out what this length is. This is just going to be the square root of 3 squared plus 2 squared, because that's the hypotenuse, and these two are, yeah, you get it. So VF minus VI is actually going to be equal to 3.61 meters per second. We know that the acceleration is VF minus VI, that vector, divided by my change in time. Well, we just found VF minus VI. It's 3.61 divided by a change in time, or sorry, yeah, divided by the change in time. Well, the change in time is 3 seconds, so we're going to divide that by 3. And we're going to get the acceleration vector is 3.61 divided by 3, which is 1.20, I'm rounding it up there, meters per second squared. Now I need the direction. The direction doesn't change when you divide, it just changes the length. So all I got to do is I got to find now the direction for this vector here. So because this is a cardinal direction already here, I'll toss in a coordinate grid down here at the bottom so you can see what I mean. This green one is already, it's just due north. So all I need to do is find this direction, or this angle right in here. And to do that, I can just use sine, cos, or tan. I've got opposite and adjacent, so I'm going to use tangent. Call that theta. So tan theta equals opposite, which is 3, over adjacent, which is 2. So theta is going to equal the tan inverse of 3 over 2. So that's going to be 56.3 degrees. And if you look at this, it's north, and I went that way, so it's going to be 56.3 degrees west of north. So our final answer down here in pink, the acceleration of our object is going to be 1.20 meters per second squared, 56.3 degrees west of north. That is subtraction of vectors. So for this one, I am only going to do one video today because this lesson is so long. It's an hour. And there's a lot of homework I want you to practice. I want you to do the sine law stuff. I want you to do the cosine law stuff. I want you to do the addition of vectors. And then there's a couple more questions back here I want you to do as well. Okay. I want you to do question number 2. It's a 4-parter. I want you to do question number 7. It's a 2-parter. And I want you to do question number 8, also a 4-parter. So there's lots of homework for this one, but again, I'm only doing one video today. There's 2, there's 7, there's 8. Give this stuff a shot. If you have any questions at all about this stuff, please, please do ask. These skills that we're doing in today's lesson are going to be vital for, I want to say 2/3 of the course moving forward here, okay? So it's important that you get this stuff down. Good luck. Come see me if you have questions. May the force be with you.